Hey friends, welcome to my channel, and in this video I am going to discuss about a problem from organic chemistry. This came in CSIR exam June 2017. This is from set A, question number 84. So you can see this is the problem given. So the molecule is start butyl acetoacetate, and it is first it is treated with sodium hydride, and second condition this compound is given. So here it is a bromine, and so you will get compound A, and then on treatment of trifluoroacetic acid you will get compound B. So there are four options given. Now this problem is not very complicated, but today I will tell you that when you get such type of problem you have to answer this very quickly, and this question, the options which are given in this case, you can do this question without solving it in details. This is a very simple question. So how should you do this I will tell you today, because in these competitive exams you don't have much time for thinking and for explaining all the things, because you have to correct the right answer, and whenever you get such type of question you have to do it very quickly within 1 or 2 minutes. So if you look at the options given, so first of all, what will happen? So sodium hydride is a base, so it will form an enolate from here. Now you can see there are two enolizable protons. One is here and one is here, but you can see this is active methylene group. So obviously when you treat this compound with base, the enolate will always generate from this side, because this proton is much more acidic. So you will get this enolate. Now what will do this enolate? So this enolate can now attack. If the enolate is from this side, then you can easily eliminate option 3, because in option 3 you can see the alkylation is occurring from the terminal side. So this will not be the case, because enolate will always form from this side. Now this enolate can attack either this position or this position, so you have to determine where it will attack. Now generally the carbonyl groups are much more electrophilic than a normal alkyl halide, but in this case they are this halide is alpha to this carbonyl group, and when I discussed the Felkiner model, that video I told you that these alpha halogens adjacent to this carbonyl group, they are much more electrophilic than normal alkyl halides, because the sigma star orbital here interact with the pi star orbital on this carbonyl group. The pi star orbital and the sigma star orbital interact, and that lowers the energy of the sigma star orbital. So normally if the sigma star orbital has energy here, this alpha halocarbonyl compound, the sigma star orbital has a lower energy. That's why its reactivity increases. So in this case this enolate can easily attack on this alkyl halide position, that is on this particular electrophilic site. Now another reason for this is that uh, so this carbonyl group, you can see here the charge separation is much higher than this. So it is, if you call it delta minus delta plus, in this case you can represent it with a full charge separation. That is a carbonyl group, you can represent like O minus O plus. That is, the charge density is much higher at this particular site than alkyl halide. So that's why this is a hard center. This is a hard center and this is a soft center. You can see this enolate is categorized as soft enolate, because the negative charge here, actually we can represent this enolate by this. So this negative charge, you can see it is stabilized not only with this one carbonyl group, it is stabilized this both carbonyl group. That means the stabilization, the resonance makes this negative charge a soft center, so it will prefer to attack on here rather than here. So that's why between this 1, so 3 is already eliminated. Now between 1, 2 and 4 you can easily eliminate option 4, because in option 4 it is attacking on the carbonyl group, so that option will not be correct. And another way you can think that from option A to option B, you can see there is given one extra carbon, so that is not possible, because one, if you look at the structure carefully, you can see one extra carbon is there. So this is wrong. So option 4 is either way wrong. So you eliminated option 3 and 4. Now you left with option 1 and option 2, and you can see in both cases the product A is what? So in both cases the product A is this one here, and now you will have this carbonyl group, this and CO2 so this is the product in product A for both 1 and 2. Now you have to find what will be the product B. Now when you treat with a tert butyl ester, this position is a tert butyl ester, and when you treat it with trifluoroacetic acid, the ester hydrolysis will occur, and this ester hydrolysis is AAC1 type, that is sorry, not AAC1, this is ALK 1 type, that is so let's say you have this is one ester, so you have this tert butyl group. So what will happen, the acid, the trifluoroacetic acid first will protonate here, so you can see this bond can break to give you this carboxylic acid and a tert butyl cation. So due to the stability of this tert butyl cation, this hydrolysis will occur, and as this alkyl oxygen bond is breaking, so it is called a acidic, and it is in acidic condition, so a alk 1, because it is unimolecular and it is occurring in acidic condition. Okay, so the thing is that here you will get a OH group after the second step. Here you will get an OH group. Now you can see this is okay. Now this ester will not hydrolyze because it is a methyl group, and methyl group cannot form a carbocation like this. So this is the initial product of hydrolysis. Now what can it do? So you can see this oxygen, now this oxygen lone pair can attack on this carbonyl group, and if this attack occurs, what you will get? You will get 1 2 3 4 5. So you can see a 5-membered ring will be formed. Here we will have OH, and this is attacking oxygen. Here you will have carbonyl group, and here the keto group. Now here what you will have? You will have this group CO2Me. Now this oxygen can push, and this OH can go, so you will get, I am writing here only, so you will get here a positive charge. After that a proton can go from here to give you this one. I'm just writing here, so you will get this. Okay, so this is how this what OH will eliminate, and you will get this. Now what can happen next? So this proton can also go here. You will have proton source, so it will be protonated, and you will be getting this product. Okay, actually 1 2 carbon, so 1 2 carbon, and here you will have OMe. Here you will have one double bond, here you will have one double bond, here OH, and here COMe group. So you can see this product is given in option 1 only. So in option 1 B, this is the B product given, but in option 2 you can see there is the position of this methyl group is different, that is and also you can see option 2 is not correct because the tert butyl group is still there, it is not hydrolyzing. So you can see when you are giving a trifluoroacetic acid, it will always remove this tert butyl group, so you can easily eliminate option 2. So without doing this mechanism, you can say option 1 is correct answer, because here only here the tert butyl group is not there. So this is how you have to proceed while doing answer. So you can see without doing this mechanism, all this, just looking at the reaction condition, you can eliminate this option 2 3 and 4, and you can easily predict that option 1 is the right answer. So I think this video will help you to think about the question, how you have to answer, how you have to pick the correct answer by just looking at the question. So if you like the video, then share it with your friends, and also give a thumbs up, and thank you for watching.